In C1.3 we talk about metals and their uses. We use metals an awful lot in our everyday lives, and you need to know that these metals come from something called an ore, O-R-E. Ores are rocks that are economically worthwhile, so worthwhile in terms of the money, extracting metals from. Things like iron ore can be used to extract iron, and that iron can be turned into the alloy steel. We'll look at alloys again later on. And copper is another one that they discuss quite a lot in C1.3. And there's actually some new methods that we'll look at on how to extract copper. Aluminium and titanium extraction are also brought up in C1.3, but these are very expensive to extract because there's lots of stages in the process and it requires a lot of energy. As I said before, you can mix metals together to make alloys, and we'll look at alloys later on. Just like with your quarrying in C1.2 limestone, you need to think about social, economic and environmental impacts of exploiting metal ores, of mining the metal ores, and as well as mining them, we need to think about recycling them and the advantages and disadvantages of doing this. Just like we were thinking about limestone as a building material, we're also thinking about metals as structural materials. You only need to know what's mentioned in the specific subject content, but again, just like in quarrying, information might be given in exam questions that you then have to evaluate the uses of certain structural materials that you haven't studied perhaps. So we've looked at ores, which are rocks that contain metals, and if you're going to try and extract that metal, you need to make it economically worthwhile. So that ore needs to contain enough metal to make it economical to extract that metal, and this might change over time, say if the price of energy changes. The analogy that I've given to a couple of my classes is that you can think of an ore as like a chocolate chip cookie where the metal is the chocolate, and if you want to extract the metal or extract the chocolate, there's got to be enough of it to make it worthwhile, and it's got to be easy enough to get it out. Otherwise, you're going to spend a lot of money trying to extract it and you'll actually not make any profit. So the rocks, the ores, are mined from the ground, and then they'll need to be concentrated before the metal is extracted and made into its pure form. However, not every metal is found as an ore, and if a metal is particularly unreactive, something like gold, this will be found just in the earth, in the crust, as the metal itself. However, anything more reactive would be found in a compound. That compound is usually the metal combined with oxygen, and therefore you have to do chemical reactions to try and extract that metal. You are given a copy of the reactivity series on your datasheet in the chemistry exam, so you can see which metals are unreactive, things like silver, gold, platinum, that you know will be found in its native state in the ground as the metal itself, and you know which ones, things like calcium, magnesium, aluminium, zinc, iron, tin, they're often going to be found in compounds in ores, and you'll then have to extract them. You need to be able to describe these ways of extracting metals, so anything that's less reactive than carbon, and carbon is actually on your reactivity series, so you can look on your datasheet and see anything below carbon can be extracted from the ore, from the oxide, by reduction using carbon itself. So that means anything like a zinc, an iron, a tin, a lead ore, a copper ore can be reacted with carbon, and the reaction that happens is called a reduction reaction. So you reduce it, you remove the oxygen. So something like iron oxide would be reduced by reacting it with carbon to make just pure iron. However, anything that's more reactive than carbon, and again remember carbon is shown for you on your reactivity series on your datasheet, actually needs to be extracted in a different way, and it needs to be extracted using a process called electrolysis. Electrolysis is just using electricity to try and extract and purify the metal. It's got to be in its molten form, and molten means that it's been melted, it's turned into the liquid instead of the solid metal ore. The problem with this is that actually electrolysis, using electricity, uses a large amount of energy, so that makes it a lot more expensive to extract these metals than the ones where you can just use reduction. You've got to know quite a bit about copper, and there's a few different ways in which you can extract your copper. So two of the main ways: if you have a copper rich ore, so if there's a lot of copper metal in the ore, then you can do something called smelting, which is just heating it up. So smelting sounds like melting, to do with heating. Or you can purify it by using electrolysis. So that's again using electricity to extract the pure copper. These copper rich ores, the ores with a lot of copper in, have quite a limited supply, so there's really not very much of them. And that's why we've had to start looking at new ways of extracting copper from low-grade ores, so ores that only have a little bit of copper in them. And the two ways that we extract copper from low-grade ores, where there's only a little bit of copper, are phytomining and bioleaching. All you need to know about phytomining is that it's using plants to absorb metal compounds, and then you burn the plants to make ash that contains those metal compounds. So it's just a way of kind of concentrating those metal compounds. It doesn't actually extract the copper, it concentrates those metal compounds so that you then have essentially a high grade ore, or a copper rich ore with lots of copper in it, that you could then go on and do smelting or electrolysis with. Bioleaching is using bacteria, and that again produces these metal compounds, the copper compounds, that can then have the copper extracted from them. All of these ways of extracting copper need remembering, so try and give yourself a little bit of help. Smelting sounds like melting is to do with heating. Then you've got electrolysis, sounds like electricity, it's using electricity to extract the copper. Phytomining sounds like photosynthesis, sounds like P for plants, so remember that it's plants doing that. And bioleaching, with a B as in bio, as in bacteria, is another way. So remember those four ways. You can also use something called displacement. So copper can be got from solutions of copper salts by electrolysis or by displacement using scrap iron. Let's just look at that in a bit more detail. A solution of a copper salt would be something like copper sulfate, and you can do electrolysis on that copper sulfate to get the copper, so you can use electricity, or you can do this thing called displacement. And displacement is what happens if you have a metal that is more reactive than the copper in the copper sulfate. So in this case we're talking about iron. Again, refer back to your reactivity series. We've got our iron and we've got copper. Iron is much more reactive, so if you have iron and copper sulfate, the iron will displace the copper, it will remove the copper from the copper sulfate, and your products are going to be the pure copper and iron sulfate salt. So iron plus copper sulfate turns into copper plus iron sulfate. That's a displacement reaction where you swapped over the two metals because iron is more reactive. This is a really good way, and actually quite a cheap way, of extracting copper, because if you can use scrap iron, so iron maybe from old cars that's going to be thrown away anyway, that's a really cheap way of extracting this copper. So moving on from copper and now looking at aluminium and titanium. The specification says you don't need to know the details of how to extract these metals, but again you might be given information in the exam where you'd have to evaluate or comment on that information about the chemical process used to extract aluminium and titanium. What you do need to know is that they can't be extracted by reduction with carbon, so that cheap way that we had where we could do reduction and take them out of their oxide ore isn't possible with aluminium and titanium. And actually the way that we do extract them is really expensive because there's lots of stages in the process and we need a large amount of energy. That could easily be a couple of marks on a question about aluminium and titanium extraction. If the question was, for example, why is it expensive to extract aluminium and titanium, state that it's because there's lots of stages and that a large amount of energy is needed. Because of this, it might actually be more sensible to recycle metals because extracting them uses up the limited resources. There's a finite amount, there's a limited amount of metals in the Earth's crust, and that combined with the fact that we've said it's expensive in terms of energy and it affects the environment negatively is making people think that actually we should be recycling instead. The only disadvantage of recycling is that you do have to collect together the materials and you do have to sort them out so that they can be separated and recycled. We said that we'd come back to alloys. Alloys are where you have a mixture of metals, so a diagram is quite a useful way of thinking about this. So in a pure metal, all of the metal atoms are arranged in nice neat rows. This means that those rows can slide over each other, and we say that that makes our metals malleable. They can kind of be bent easily and changed in terms of their shape. If you have an alloy, that's a mixture of metals, so you've got one metal here and a different type of metal here. And those metal atoms are going to be different sizes, so that distorts or it changes the structure of your material. And actually here you can see that it would be very difficult for a layer to slide over and change the shape. So we say that actually our metals, things like pure copper, gold, iron and aluminium, are actually too soft, they're too malleable to be used a lot of the time. But if you mix them with a small amount of similar metals, so that's the other metals here, then that makes them a lot harder, it makes them a lot stronger. One of the specific examples of this is iron. So iron can be obtained from the blast furnace, so by reducing it from its iron oxide or removing the oxygen from the iron oxide ore, and that iron actually has about 96% iron in it. There are some impurities and that makes it really brittle, so it actually can't be used that easily. So most of our iron is converted into something called steel instead. Steel is an alloy. Alloy is, in this case, the iron mixed with carbon. So you have those different metals, those different atoms that will give it this changed structure that means it's much stronger. Actually, we can design our alloys to have specific uses. So if it's low carbon steel, it's only got a little bit of carbon compared to the iron, then we can shape that easily. If you have a high carbon steel, actually that's going to be much harder and much stronger. And then something like stainless steel, that things like knives and forks and things in your kitchen might be made of, these have really good properties in that they are resistant to corrosion, they're unreactive, and they won't rust, for example. You also need to know about the properties and uses of metals. When we say properties, we're just talking about the words that we would use to describe them and how they act. So the ones that we're particularly interested in are the ones in the centre of the periodic table, the transition metals. So the transition metals are all of these ones in the centre of your periodic table, and you need to know about some of the properties of these. The transition metals are really good conductors of heat and electricity, and they can be bent or hammered into shape. We can say they are malleable. They're really good for making structural materials, so using in buildings, and for making anything really that needs heat or electricity to pass through it. So things like copper can be used in electrical wiring and in plumbing. The reason why it's used in plumbing is because the copper does not react with water, it's very unreactive. Things like aluminium and titanium have a low density, they're very light, and again they're resistant to corrosion, they do not react, they're unreactive, and this makes them very useful. So your key properties are that they're unreactive, they might resist corrosion or not react with water, they're malleable, they can be bent and hammered into shape, they have a low density so they can be used for things like aircraft, and they are good conductors of heat and electricity. So all of your transition metals in the centre of the periodic table tend to have these properties, and you could get asked a question about what the properties are and how you'd link that to their uses.